Module 3, Lecture A, Baselines and Metrics. By the end of this lecture, you will be able to create baseline predictors for regression and classification engineering problems, implement mean-squared error, accuracy, precision, recall, F1 score, and confusion matrix manually, and interpret metric results in terms of engineering risk, cost, and decision quality. Baseline models. Regression baselines. A regression baseline is a simple predictor for continuous values used as a benchmark for more complex models. In engineering, it might predict outcomes such as energy use or machine temperature using a basic rule like the historical average. If a machine learning model does not clearly outperform this baseline, its added complexity may not be justified. Common regression baselines make simple predictions using summaries such as the mean, the median, or the most recent value. The mean works well when errors are balanced, while the median is more robust to extreme outliers. For time-sensitive data, a persistence baseline predicts that the next value will match the last observed one. These baselines are easy to explain, fast to compute, and useful for comparison. Regression baselines show whether a model truly improves prediction or only adds unnecessary complexity. In engineering, a more complex model must clearly outperform the baseline to justify its cost, especially when decisions affect safety. Baselines also help reveal problems such as weak features, poor modeling choices, or data leakage. Starting with a baseline makes later models easier to judge and more reliable for real-world use. Python code, regression baselines. Regression baselines provide simple benchmarks for judging prediction performance. In engineering tasks, they offer practical comparison points, such as using the mean or median as a basic reference. We import NumPy for efficient numerical calculations with arrays, and matplotlib pyplot for creating clear visualizations of data and results. We store small pump energy readings as numerical arrays for model evaluation. The training set contains several kilowatt-hour observations, including one much larger value, while the test set contains 4 similar readings. These data will be used to assess how well baseline predictions perform. Before running calculations, check that the training and testing arrays are not empty and that each one is one-dimensional. These simple validations confirm the data is in the expected form and help prevent errors later in the code. We create 2 simple baseline predictors by finding the average and the median energy use in the training data. These values represent typical past energy use and can be used as basic predictions to compare against more advanced models. We create baseline predictions for the test data by filling arrays with a single repeated value, either the mean prediction or the median prediction. This gives every test case the same baseline estimate, making it easy to compare these simple predictors with the actual test values later. This function measures prediction accuracy using mean-squared error. It compares each actual value with its predicted value, squares the differences to focus on error size, and then averages those squared errors. The result is a single floating point value, where smaller values indicate better predictions. We evaluate simple regression baselines by measuring their mean-squared error on the test data. One baseline predicts using the training data mean, and the other uses the training data median. Comparing these predictions with the actual test values shows how much error each baseline makes on average. The output reports 2 simple baseline predictions, the training data average and the training data median, both shown in kilowatt hours. It then compares their accuracy on the test data using mean squared error, which averages the squared differences between actual values and each baseline prediction. This lets us see whether the mean or median baseline performs better. To choose the better baseline prediction method, compare the test mean squared error for using the mean versus the median. If the median has the lower error, use it as the baseline. Otherwise, use the mean. The result identifies which simple baseline performs better for later analysis or implementation. This plot compares actual pump energy use during the test period with two simple regression baselines. The x-axis is a sequence of test days, and the y-axis shows energy use in kilowatt hours. The chart displays the actual values alongside mean and median baseline predictions, using different markers and a legend to distinguish them. Axis labels, a title, and a light grid make the comparison easier to read before the plot is displayed. This script creates simple regression baselines for pump energy use by predicting test values with the training data's mean and median. It compares the two baselines using mean squared error and reports which one performs better. It also plots the actual test values against the mean and median predictions to make the comparison easier to interpret. Regression baselines. A regression baseline is a simple way to predict continuous values and compare against more complex models. It often uses the average target value from the training data as the prediction for new cases, such as estimating future engineering measurements from past data. If a more advanced model does not clearly beat this baseline, it may point to problems with the model, the input features, or the data. Regression baselines are simple benchmarks built from summaries, rules, or domain knowledge. A median may work better than an average when extreme outliers are present, while time-dependent data can use the last observed value as the next prediction. In engineering settings, baselines may also come from design rules, manufacturer specifications, or basic physical estimates. These simple methods show what performance is possible before using more complex models. A regression baseline gives a model a clear benchmark for judging performance. Without one, an error value is hard to interpret because it may or may not improve on a simple approach like using the average. In engineering decisions such as shutdowns or maintenance planning, this comparison helps show whether a more complex model is worth using and makes its value clear to stakeholders. Python code. Regression baselines. Regression baselines provide simple reference predictions so engineering teams can judge model performance clearly. In this example, the task is to predict pump flow rates. We import NumPy for efficient numerical work with arrays and mathematical operations. We also import matplotlib's plotting tools to create graphs and charts for visual data analysis. We create a small deterministic training dataset for the pump problem by pairing operating times with their corresponding flow rates. The time values represent pump hours, and the flow values give the gallons per minute for each time interval. This known set of input and output pairs is then used to train regression models. We set up a small test dataset to evaluate pump flow predictions. It includes selected test times, such as 15 through 75 hours, along with the actual flow rates at those times, ranging from 100 to 104 gallons per minute. These true values let us compare the model's baseline predictions with real data. Before training or evaluating the model, we check that each set of input hours has the same number of matching flow values. This prevents features and targets from becoming misaligned during training and ensures every test input has a true value for accurate evaluation. To create simple regression baselines, we compute the mean and median of the training flow data. The mean gives an overall average, while the median provides a central value that is less sensitive to outliers. Both are converted to standard numeric values and used as baseline predictions to compare against the test data. To create simple baseline predictions for the test cases, we assign every test case the same previously calculated mean value, and separately the same median value. These prediction sets match the size of the test data, making them easy to compare with the actual results. Mean squared error measures how accurate predictions are by comparing them with the actual values. It finds the errors, squares them to make them positive, and give more weight to larger mistakes, then averages the squared errors into one overall score. A lower value indicates better prediction quality. This line calculates the mean squared error as a floating point value. It compares actual and predicted values, squares the differences, and uses the NumPy mean function to average them. This gives a standard measure of prediction error in regression tasks. We evaluate two simple baseline strategies using mean squared error. By comparing the actual test flow values with predictions from the mean baseline and the median baseline, we get a clear measure of each method's prediction accuracy and can compare their performance. The code compares two simple baseline predictions for pump flow, the mean and the median, reported in gallons per minute. It then prints the mean squared error for each baseline to measure prediction accuracy. The lower the mean squared error, the better that baseline performs as a simple decision strategy. A new plotting area is created to compare pump flow over time. The actual test flow values are shown against the test hours, and the mean baseline predictions are plotted on the same timeline. This makes it easy to visually judge how closely the baseline predictions match the true flow data. The plot compares median baseline predictions with test hours using a dashed line and diamond markers. The axes identify operating time in hours and pump flow in gallons per minute, and the title makes clear that the visualization shows regression baselines for pump flow. The plot is finalized by adding a legend to distinguish actual flow from the mean and median baseline predictions. A subtle grid improves readability, and the layout is adjusted so the figure fits cleanly. The completed plot is then displayed for visual comparison of the test values against the baseline predictions. This script tests simple baseline models for predicting pump flow rates using the average and median flow from the training data. It compares these constant predictions with the test data using mean squared error to see which baseline performs better. It then reports the predictions and errors and plots the actual test flow alongside both baselines for a quick visual comparison. Baseline predictor types. Baseline predictors are simple reference models used to judge whether a more complex machine learning model is actually useful. In regression, they might predict the average or median target value, while in classification, they often predict the most common class. Their purpose is not to be sophisticated, but to set a minimum performance level that better models should exceed. Baseline predictors provide simple reference points for judging a model. Constant baselines reveal issues like class imbalance, while random or stratified baselines show whether the model performs better than chance while respecting class frequencies. Rule-based baselines add basic domain knowledge, giving a more practical comparison than simple guessing. Choose a baseline predictor based on the problem context and how the model's output will be used. For regression, a historical average may work, while the median can be better when extreme values are present. For classification, predicting the most common class can be misleading, especially with rare events, because it may not test useful decision-making. A strong model should outperform these simple baselines. If it does not, the features, data quality, or problem definition may need to be reconsidered. Python code. Baseline predictor types. Baselines provide simple comparison points for engineering decisions. By comparing regression and classification baselines, metrics help show whether those baselines are useful. We begin by importing NumPy, a key Python library for efficient numerical computing. In this script, it supports arrays, statistical calculations, and random number generation, which are needed to build and evaluate baseline predictors for regression and classification tasks. We set a fixed seed for NumPy's random number generator so random results are repeatable each time the code runs. This makes testing and comparing baseline models consistent and reliable. We create a NumPy array to store energy consumption target values measured in kilowatt hours. This makes it easy to run statistical and vectorized calculations when evaluating baseline regression models. First, the program checks that the regression target data for energy use in kilowatt hours has at least 4 values. If there are fewer than 4, it raises an error and stops. This protects data quality and ensures later statistical calculations use enough data to be meaningful. A constant regression baseline predicts the same value for every data point. Here, one baseline uses the mean of the energy data, and another uses the median. These simple constant predictions provide benchmarks for judging whether more complex models perform better. Mean squared error is a common way to evaluate regression models. It measures how far predictions are from the actual values by finding the differences, squaring them to emphasize larger mistakes, and then averaging the results. The final value represents the average squared difference between actual and predicted values. We create a small set of pass and fail labels to inspect classification results. These labels represent the true outcomes and help us evaluate how well baseline classification models perform. Keeping the set small makes the model behavior easier to understand. The code verifies that there are at least 4 classification labels before continuing. This safeguard helps ensure there is enough data for meaningful predictions and comparisons, and stops the analysis if the requirement is not met. To create a simple classification baseline, first find the unique labels in the actual data and count how often each one appears. The most frequent label becomes the majority label. Then make a prediction array where every entry is set to that label, giving a basic benchmark for comparing classification accuracy. To make a stratified prediction, first estimate each class's proportion by comparing its count to the total number of labels. Then randomly choose predicted labels using those proportions, so the predictions follow a similar class distribution to the observed data. The accuracy function measures how often classification predictions match the true values. It compares the predicted and actual labels, marks each match as correct or incorrect, and then averages those results. This average gives the proportion of correct predictions, which is the model's accuracy. We report simple baseline results for both regression and classification. For regression, we compare constant predictions using the mean and the median, measuring each with mean squared error rounded to 2 decimals. For classification, we compare a majority class baseline with a stratified baseline, reporting accuracy rounded to 2 decimals. The key caution is that accuracy may not be enough when rare failure cases matter, so more detailed evaluation metrics may be needed. This script tests simple baseline models for regression and classification. For regression, it predicts energy use with constant mean and median values and compares them using mean-squared error. For classification, it predicts either the majority class or class proportions and measures accuracy. These baselines provide a basic benchmark, while also showing that accuracy alone can miss important details, especially when rare events matter. Manual metric calculations, mean-squared error. Mean-squared error is a common way to evaluate regression models that predict continuous values. It measures the average of the squared differences between predicted and actual values, so larger mistakes count more heavily. This makes it useful in engineering tasks, such as energy consumption prediction, where big errors can increase cost or risk. Mean-squared error is found by comparing each prediction with its actual value, squaring the errors, and averaging them across all observations. Because larger mistakes grow more after squaring, this measure shows both overall model accuracy and the impact of serious errors. For example, large underestimates in machine cycle time predictions would raise the mean-squared error and warn of possible scheduling or production problems. Mean-squared error is useful for comparing models on the same dataset, but its units are squared, so it can be harder to interpret directly. In general, a lower value means better performance, but how much that improvement matters depends on the situation. Small gains may be important in high-stakes predictions, while the same change may matter less in lower-stakes tasks. Python code, mean-squared error. Manual metrics help evaluate engineering models. Mean-squared error is useful because it gives larger penalties to bigger prediction errors, such as misses in machine cycle minutes. We define a list of actual machine cycle times, measured in minutes, using 5 real-world values. These measurements provide the baseline for comparing predicted cycle times and evaluating prediction accuracy with metrics such as mean-squared error. Predicted machine cycle times are stored as a list of durations in minutes. These values are kept so they can be compared with actual cycle times, allowing errors to be calculated and the predictive model's accuracy to be evaluated. The code first checks that the actual and predicted cycle time lists have the same length. This confirms that every actual value has a matching prediction for the error calculation. If the lengths differ, it raises an error and stops the mean-squared error calculation. The code first checks whether any actual cycle time observations are available. If the list is empty, it raises an error, stating at least one observation is required. This prevents later calculations from running without data. To analyze prediction accuracy, we collect the error for each observation by comparing the predicted cycle time with the actual cycle time. For each pair, the actual value is subtracted from the predicted value, and the result is stored. This creates a complete set of prediction errors for later analysis. To prepare for mean-squared error, each prediction error is squared and stored in a new list. Squaring makes all errors non-negative and gives larger mistakes more weight, which helps measure overall prediction accuracy. Mean-squared error is found by averaging the squared differences between predicted and actual values. First, count how many squared errors there are, then divide their total by that count. This gives a common measure of prediction accuracy. Taking the square root of the mean-squared error gives the root mean-squared error. Because it is measured in the original units, such as minutes, it is easier to interpret and shows the typical size of prediction errors. The output compares actual and predicted cycle times, then shows the prediction errors and their squared values. It reports the mean-squared error, rounded to 3 decimal places, as the average squared difference in squared minutes. It also reports the root mean squared error in minutes, making the result easier to interpret. The key reminder is that large errors can strongly increase mean squared error and may affect production schedules. This script measures how well predicted machine cycle times match actual times using mean squared error and root mean squared error. It first confirms the 2 time lists are valid, then compares each prediction with the actual value, squares the errors, and averages them. The root mean square error gives the result in the original time units, making it easier to interpret. The output shows how large prediction mistakes can raise error metrics and potentially disrupt production schedules. Classification metrics. Classification metrics start by checking whether each prediction matches the true class label. In binary classification, each observation belongs to one of 2 possible classes, and accuracy is the share of predictions that are correct out of all predictions made. To calculate it manually, compare every predicted label with its actual label and count all correct matches, making sure no observations are left out. A confusion matrix summarizes classification results by showing which predictions were correct and which were errors. In binary classification, each result is labeled as a true positive, true negative, false positive, or false negative, depending on the chosen positive class and the actual outcome. This helps analysts see not only how often a model is wrong, but what kinds of mistakes it makes. When classes are imbalanced or mistakes have different costs, accuracy alone can be misleading. A model may look strong by mostly predicting normal cases while still missing rare but critical failures. Confusion matrix metrics reveal the balance between correct negatives, correct positives, false alarms, and missed problems, helping assess real risk and cost in areas like quality control and cybersecurity. Python code classification metrics. Manual metrics help evaluate the quality of classification decisions by counting outcomes directly. This matters because different engineering errors can have very different consequences. We define a list of actual labels to store the true classifications of inspected parts. Each value marks a part as positive or negative, providing the ground truth needed to compare against predictions and evaluate a classification system. The predicted labels list stores the inspection system's binary predictions for each item. A 1 means a positive prediction, and a 0 means a negative prediction. These predictions can later be compared with the actual labels to evaluate the system's performance. Before computing classification metrics, the code verifies that the actual labels and predicted labels have the same number of entries. This ensures every prediction matches one true label. If the lengths differ, it raises an error to prevent inaccurate metric calculations. We begin by setting up counters to evaluate a classification model. These counters track correct positive predictions, correct negative predictions, and cases where the model incorrectly predicts a positive label for a negative example. Starting them at 0 prepares us to manually tally the model's performance. A false negative counter is initialized to 0 to track cases where the true label is positive but the model predicts negative. This count is important for measuring how often the model misses positive cases, especially when calculating recall. To count true positives, compare each actual label with its matching predicted label. When both labels are 1, the model has correctly identified a positive case, so the true positive count increases by 1. This total shows how often the model correctly predicts positive outcomes. This code checks for true negatives by seeing when both the actual label and the predicted label are 0. When that happens, it increases the true negative count by 1. showing that the system correctly identified a non-defective part. This code checks for a false positive, which happens when the true label is negative, but the model predicts positive. Each time this occurs, it adds 1 to the false positive count. Tracking this count helps measure how often the system mistakenly labels negative cases as positive. This code checks for a false negative, which happens when the true label is positive, but the model predicts negative. When that occurs, it increases the false negative count by 1. Tracking these missed positive cases helps evaluate model performance, especially when failing to detect positives is important. To evaluate the predictions, first count the total cases from the number of actual labels. Then, find the correct cases by combining true positives and true negatives. Finally, count the predicted positives by combining true positives and false positives, which shows how many instances were labeled positive overall. The total number of actual positive cases is found by adding true positives and false negatives. True positives are correctly predicted positive cases, while false negatives are positive cases that were missed. Together, they show how many cases were truly positive, regardless of the model's prediction. The code evaluates model performance using 3 metrics. Accuracy shows the overall share of correct predictions. Precision shows how many predicted positives were truly positive. And recall shows how many actual positives were correctly found. It also checks for 0 counts before calculating precision or recall to avoid division errors. The F1 score combines precision and recall by multiplying them together, doubling the result, and dividing by their sum. If precision and recall both add up to 0, the F1 score is set to 0, so the calculation stays valid and avoids division by 0. We summarize the confusion matrix by reporting correct predictions as true positives and true negatives, along with errors as false positives and false negatives. We then calculate accuracy, the share of all cases classified correctly, and precision, the share of positive predictions that were correct. Both metrics are rounded to 3 decimal places to make the model's performance easier to read. Report, recall, and F1 score rounded to 3 decimal places to summarize model performance. Recall shows how many actual positives the model correctly finds, while the F1 score balances precision and recall. Also consider the practical costs. False positives can waste inspection labor, and false negatives can let defective parts pass inspection. This script evaluates a classification system by comparing actual labels with predicted labels. It counts true positives, true negatives, false positives, and false negatives, then uses those counts to calculate accuracy, precision, recall, and the F1 score. The printed results summarize overall performance and show how false positives and false negatives can affect inspection workload and quality control. Precision, recall, F score. Precision, recall, and the F score help evaluate classification models, especially when positive cases are rare or costly. They are based on the confusion matrix, which separates correct and incorrect predictions. Precision measures how many predicted positives are truly positive, making it important when false alarms are expensive or risky. In predictive maintenance, low precision means many machines are flagged unnecessarily, wasting resources and reducing trust in the model. Recall measures how well a model finds the cases that are truly positive. What matters when missing them could be costly or dangerous. High recall helps catch most important cases, such as patients with a condition or hazardous engineering readings, but it can reduce precision by marking more borderline cases as positive. Changing the decision threshold controls this trade-off. A more cautious threshold raises recall, while a stricter one improves precision but may miss some true positives. The F1 score combines precision and recall into one measure, making it useful when both false alarms and missed cases matter. It favors models that balance these two metrics, such as in defect detection or fraud monitoring. Always define the positive class clearly because it changes what precision and recall mean. In practice, choose metrics based on real-world costs and risks, since a model with a lower F1 score may still be better if it fits the system's risk tolerance. Python code, precision recall, F-score. Manual metrics help show the trade-offs behind engineering decisions. Here, the positive class is machines that need maintenance, and the basic counts are used to calculate precision, recall, and F1. We define a list of true equipment states, where each label shows whether a machine needs maintenance or not. These actual values are later compared with the model's predictions to evaluate performance. The code creates a list to store the model's maintenance predictions for each machine. A value of 1 means maintenance is predicted, while 0 means it is not. These predictions can then be compared with the machine's true conditions to evaluate the model's performance. Before comparing results, confirm that the true equipment states and predicted maintenance alerts have the same number of entries. This ensures each prediction matches one true state. If the lengths differ, an assertion error signals a data mismatch. To manually build a confusion matrix, count 4 types of prediction outcomes. True positives are cases where both the actual label and the prediction show maintenance is needed, while false positives are cases where the model predicts maintenance when it is not needed. False negatives occur when maintenance is needed, but the model misses it, and true negatives occur when both labels correctly show no maintenance is needed. Together, these counts summarize how well the prediction model performs. The safe divide function divides a numerator by a denominator, while avoiding division by 0 errors. If the denominator is not 0, it returns the normal result. If it is 0, it returns 0.0, so the program can continue running smoothly. Precision measures how reliable maintenance alerts are by comparing correct alerts with all alerts raised. Recall measures how many actual failures were correctly detected. The F1 score combines precision and recall into one balanced measure of overall alert quality. We evaluate the model by reviewing the confusion matrix and key metrics: precision, recall, and the F1 score. Precision shows how reliable the maintenance alerts are. Recall shows how many real failures the model catches, and the F1 score balances both. These measures matter because false positives can cause unnecessary inspections, while false negatives can lead to unplanned downtime. This script evaluates a machine maintenance prediction model by comparing actual equipment states with its alerts. It counts correct and incorrect predictions, then uses them to calculate precision, recall, and the F1 score. Precision shows how trustworthy the alerts are. Recall shows how many real failures are detected, and the F1 score summarizes the balance between them. These metrics help reveal the trade-off between unnecessary inspections and missed failures that could cause downtime. Model evaluation should focus on the errors that matter most in context, not just a single overall score. In classification, missing a real failure can be risky, so recall may be critical, while false alarms can create unnecessary cost and disruption. In regression, both the size and direction of errors matter, because underestimates and overestimates can have different consequences. Choose metrics that reflect the system's most important risks. Evaluate a model's metrics in the context of how its outputs will be used. Errors may be acceptable when the model only helps prioritize human review, but they must be rare when the model controls critical processes. Consider whether mistakes are isolated or could cause wider problems, and use real-world decision quality to judge whether the model reduces risk or needs safeguards before deployment. Python code, failure risk. Metrics help reveal the risk of engineering failures, which can be costly if missed. Baselines provide a reference point for judging the quality of decisions. The script starts by importing NumPy, a Python library used for efficient numerical computing. It supports array handling and mathematical operations needed later for calculating engineering failure risk metrics and costs. The code stores the true pump failure labels in a NumPy array, using 1 for failure and 0 for no failure. These ground truth labels are later used to evaluate how well different inspection policies perform. 2 inspection policies are defined as arrays for later evaluation against the true pump failure labels. One is conservative, marking most pumps as failed to avoid missing problems, while the other is riskier, marking fewer pumps as failed and assuming most are working correctly. The code verifies that the true pump failure labels and both inspection policy arrays are the same length. This makes sure each policy can be compared correctly against the true labels. If the lengths do not match, the assertion stops execution and immediately signals the problem. The metrics function calculates key classification results by comparing true labels with predicted labels. It counts true positives as correctly predicted failures where both labels indicate 1, and true negatives as correctly predicted non-failures where both labels indicate 0. The code measures 2 key error types in the inspection policy. False positives occur when the system predicts a failure even though none occurred, while false negatives occur when it misses a real failure. Together, these counts help evaluate how well the policy identifies failures. The code evaluates model performance using accuracy and precision. Accuracy measures the share of all predictions that were correct, based on true positives and true negatives. Precision focuses only on positive predictions, showing how many predicted positives were actually correct. Recall measures how well a model finds actual positive cases by comparing true positives with all real positives, including missed ones. The F1 score combines precision and recall into a single balanced measure. In both calculations, a small safeguard is used to prevent division by 0 and keep the results numerically stable. The function summarizes a classification model's performance by returning the main confusion matrix counts: true positives, true negatives, false positives, and false negatives. It then reports accuracy, which measures overall correctness, precision, which measures how many positive predictions were correct, and recall, which measures how many actual positives were found. Finally, it returns the F1 score, which balances precision and recall into one metric. We evaluate both inspection policies by comparing their predictions with the true failure labels using the metrics function. For each policy, it reports key classification results such as correct and incorrect predictions, accuracy, precision, recall, and the F1 score. These metrics let us compare the conservative and risky policies in a consistent way. We assign a high cost of 100,000 to a false negative because missing a real failure is very expensive. A false positive, or false alarm, is assigned a lower cost of 8,000. These costs will be used to compare the expected cost of different inspection policies. To compare the safe and risky inspection policies, calculate the expected cost of their mistakes in the same way. For each policy, multiply false negatives by the cost of a missed failure, 100,000, and add false positives multiplied by the false alarm cost, 8,000. The resulting totals show the financial impact of each policy's errors. The output compares conservative and risky policies using key metrics such as accuracy, precision, recall, F1 score, false negatives, false positives, and total cost. Each policy's results are formatted for easy reading, with performance scores rounded and costs shown clearly. The main takeaway is that missed failures drive most of the cost and safety risk, so reducing false negatives is especially important. This script compares conservative and risky pump inspection policies by measuring how well each predicts failures. It reports performance metrics such as accuracy, precision, recall, and F1 score, then adds costs for false alarms and missed failures. Because missed failures are much more expensive, the total cost shows that the conservative policy is safer in this setting, even if it predicts more failures. Cost-sensitive metrics. Cost-sensitive metrics matter when different prediction errors have different consequences. In engineering, a model should be judged not only by how often it is correct, but by the cost of being wrong. A false alarm may waste resources, while a missed warning can cause serious damage or downtime. Cost-sensitive evaluation therefore focuses on money, safety, and reliability, not just simple accuracy. Cost-sensitive evaluation can change which model is best, because accuracy alone may hide the impact of different errors. A slightly less accurate model may be preferable if it avoids mistakes that are costly or dangerous, such as missing a defective medical part or failing to warn about a severe flood. Precision and recall should therefore be judged in context, based on which errors are acceptable and which must be minimized. Cost-sensitive metrics help engineers choose models based on real-world impact, not just high statistical scores. They make the costs of action and inaction explicit, including safety and trust concerns as well as money. By reviewing the confusion matrix with domain experts, teams can decide which risks are acceptable and which errors are too serious. Python code, cost-sensitive metrics. Cost-sensitive metrics show how model errors translate into real engineering consequences. In this example, two turbine warning models are compared, with manual calculations used to make the evaluation clear and transparent. This line indicates that the script runs using only standard Python libraries. No extra installations or dependencies are needed, so the code is easy to run in a basic Python setup. We store the actual turbine fault labels as the ground truth for evaluation. Each label shows whether a fault occurred at a given time, using 1 for a fault and 0 for no fault. These true labels are used to measure how well the turbine warning models perform. The script stores binary fault predictions from two turbine warning models, where 1 means a predicted fault and 0 means no fault. These predictions are kept separately from the true fault labels, so the models can be compared. This organization makes it easy to evaluate each model later, using performance metrics and cost calculations. We assign costs to operational errors to evaluate models in a cost-sensitive way. A false alarm costs 800, while a missed fault costs 12,000 because failing to detect a real fault can lead to serious downtime or damage. These values help compare model performance based on practical consequences, not just accuracy. The confusion counts function manually computes key parts of a confusion matrix by comparing actual and predicted values one by one. It first checks that both lists have the same length, then counts cases where both values are 1 as true positives and cases where both are 0 as true negatives. This makes the model evaluation process clear and transparent. The code compares actual and predicted values to count classification outcomes. A false positive occurs when the actual value is 0, but the prediction is 1, while a false negative occurs when the actual value is 1, but the prediction is 0. It then returns the counts of true positives, true negatives, false positives, and false negatives to help evaluate model performance. The evaluate model function uses confusion counts to find true positives, true negatives, false positives, and false negatives, showing how predictions compare with the actual labels. It then counts the total observations and calculates accuracy as the share of correct predictions, combining true positives and true negatives. Precision measures how many predicted positives were correct, while recall measures how many actual positives were found. The F1 score combines precision and recall into one balanced measure using their harmonic mean. If any required denominator is 0, the corresponding metric is set to 0 to avoid division errors. The model's error cost is estimated by combining the cost of false alarms with the cost of missed faults. The output then reports the model name, key performance metrics such as accuracy, precision, recall, and F1 score, plus the counts of false positives and false negatives. Finally, the calculated cost is returned, so different models can be compared by their financial impact. We evaluate Model A and Model B by comparing each model's predictions with the true labels using the evaluate model function. This produces a cost for each model based on the predefined penalties for false alarms and missed faults. These costs let us compare the models in terms of their engineering impact. Compare the engineering costs of Model A and Model B. Then select the model with the lower cost as the cost-sensitive choice. This result is reported as the preferred model. The key reason is that missed faults are especially costly because they can lead to expensive downtime. So reducing missed detections is the priority. This script compares two turbine warning models using both standard performance metrics and cost-sensitive evaluation. It calculates confusion matrix results, then reports accuracy, precision, recall, and F1 score for each model. Because missed faults are much more costly than false alarms, the final recommendation is based on the model with the lower estimated cost. The key takeaway is that reducing missed faults is especially important because they carry a high risk of downtime. Decision threshold tradeoffs. A decision threshold turns a model's probability score into an action, so it is just as important as the model's accuracy. Lower thresholds catch more possible problems but create more false alarms, while higher thresholds reduce false alarms but may miss real issues. To interpret model metrics correctly, you must consider both the model's predictions and the decision rules applied to them. Decision thresholds should reflect the risks and costs of different errors. In safety-critical settings, teams may lower the threshold to reduce false negatives, even if that creates more false positives. When false positives are costly or disruptive, a higher threshold may be better. The best choice depends on error costs, follow-up effectiveness, and the organization's risk tolerance. Decision thresholds should be evaluated within the full engineering workflow, not just by overall model metrics. A model may seem accurate, but still create too many alerts or miss events that matter. Teams should compare thresholds using precision, recall, and error types, while considering real-world limits and consequences such as capacity, safety, and risk. The goal is to choose a threshold that supports responsible action in practice. Python code, decision threshold tradeoffs. Thresholds convert scores into engineering decisions. Lower thresholds detect more risky failures, while higher thresholds help avoid costly false alarms. The script imports NumPy for efficient numerical work with arrays and Matplotlib's plotting module for creating visualizations. Together, these tools support data analysis and graphical display. We store the actual pump failure outcomes in a NumPy array, using 1 for failure and 0 for no failure. This gives us the true labels needed to compare against predicted scores later. The model's pump failure risk scores are stored in an array, with each score representing the predicted likelihood of failure for one instance. These scores can then be compared with actual outcomes to evaluate prediction quality. They also support performance assessment across different decision thresholds. Before measuring model performance, the code verifies that the true outcomes and predicted scores have matching shapes. This ensures each score lines up with the correct outcome and prevents invalid calculations. An assertion is used as a safeguard, raising an error if the shapes do not match. Engineers can test risk score thresholds such as 0.3, 0.5, and 0.7 to decide when action is needed. Comparing these thresholds shows how sensitivity changes the trade-off between detecting real failures and avoiding false alarms. The function turns scores into binary predictions by comparing each one with a chosen threshold. It then counts true positives, where both the actual outcome and prediction are 1, and false positives, where the actual outcome is 0, but the prediction is 1. These counts help assess model performance across different thresholds. False negatives are cases where an actual failure is predicted as a non-failure, while true negatives are cases where both the actual and predicted outcomes show no failure. Precision measures how accurate the positive predictions are by comparing true positives with all predicted positives. Recall measures how well actual failures are captured by comparing true positives with all real failures. The function reports precision, recall, false positives, and false negatives to evaluate model performance. Precision shows how many predicted failures were correct, while recall shows how many actual failures were caught. False positives are false alarms, and false negatives are missed failures. Together, these metrics help compare threshold choices and balance catching failures against avoiding unnecessary alerts. The code compares different threshold choices by calculating key performance metrics for each one, including precision, recall, false positives, and false negatives. It repeats this process across all thresholds and stores the results together, making it easy to see how changing the threshold affects model performance. The code prints a clear header for a decision table that compares threshold values with precision, recall, false alarms, and missed failures. This formatting helps make the trade-offs between different threshold choices easier to review. For each threshold, the metrics are summarized by showing precision, recall, false positives, and false negatives. Presenting these values together makes it easier to compare threshold choices and understand the trade-off between false alarms and missed failures. We separate the threshold evaluation results into 2 lists, one for precision and one for recall. Precision comes from the first value in each result row, and recall comes from the second. These lists let us visualize how both measures change as the threshold varies. A new plot is created with a clear, manageable size. Then precision and recall are graphed against the same threshold values. Precision is shown with circular markers, while recall is shown with square markers, making it easy to compare how both metrics change as the threshold is adjusted. Label the plot so its purpose is clear. The horizontal axis shows the inspection threshold for pump failure risk, and the vertical axis shows metric values such as precision and recall. The title, Threshold Choice Changes Engineering Risk, emphasizes that changing the threshold affects risk management decisions. Set the plot's vertical range so the data fits clearly, then add a lightly transparent grid to make it easier to read. Include a legend to distinguish precision from recall, and display the plot to compare how different threshold choices affect both measures. This script shows how changing the decision threshold affects a pump failure prediction model. It compares precision, recall, false positives, and false negatives at several thresholds to reveal the main trade-off. Lower thresholds catch more failures but create more false alarms, while higher thresholds reduce false alarms but may miss failures. A plot of precision and recall across thresholds helps engineers choose a threshold that matches their risk tolerance. In this lecture, you learn to create baseline predictors for regression and classification engineering problems, implement mean-squared error, accuracy, precision, recall, F1 score, and confusion matrix manually, and interpret metric results in terms of engineering risk, cost, and decision quality. In the next lecture, Lecture B, we will go over training and testing. Thank you for your attention. See you all in the next lecture.